of machine learning and deep learning, right? So we started with this very basic probability statistics. Especially we have gone into Bayes theorem, and whenever we are going to Bayes theorem, so two types of probabilities they are actually required. So one is called as joint probability, and second is called as conditional probability. So these two are actually the workhorses of this Bayes theorem, and Bayesian analytics, Bayesian statistics, whatever you will tell, it is we are having those two things actually in many numerous forms. Now we after basically introduced into statistics and probability and all these kind of basic probabilities, how to calculate and all these things, we started delving into this prior posterior framework. Okay, so now prior posterior framework, they are also kind of this conditional probabilities and joint probabilities in some form it will be coming. Now we have looked into that when we are having that the array kind of data with us or tabulated data with us, in which different joint probabilities will be given between two or more than two events. Okay, so when it is tabulated data, then it is basically kind of very easier for us to calculate. Okay, and we are having array operations in almost all the languages, so we can actually do that very easily. Now, when it is not kind of discrete event, discrete random variables or discrete events, we are actually facing the hit. Okay, so then we will be going into different continuous distributions, and these continuous distributions are basically you can say they'll be used in form of priors, they'll be used in form of likelihoods, and the posteriors will be computed. Okay, now posteriors sometimes so before going into posteriors, basically we started looking at something called as likelihood. Okay, likelihood of the data. So likelihood of the data is basically, you can say that using a hypothesized parameter set, what is the measure or how likely a particular data set is being generated by a parameter set. Okay, so what is the measure? How we are going to measure? That is called as likelihood. So suppose I am having some kind of data available with me, and I am having some kind of hypothesis parameter with me. Okay, so what is the probability that it is not probability actually, likelihood is not considered as a probability. Okay, generally we differentiate between these two. So likelihood is basically what is the it is a basically how likely the data is being generated by that particular parameter set. So this is what likelihood is taken. So this likelihood depends upon what kind of data generating process it is. Okay, so if it is a kind of suppose categorical outcomes, then we have to look into that whether it is binary or multinomial, this kind of things. Now for that we'll be generally going into binomial, Bernoulli and all these kind of distributions. So Bernoulli, binomial, or this kind of, or multinomial kind of distributions to model the likelihood. Now if it is suppose a kind of continuous random variable, then we are going into the normal likelihood in most of the cases. Okay, in general, most general cases. Now the thing is that sometimes our aim is to, not sometimes, basically it is our aim is to maximize the likelihood. Okay, maximize the likelihood, because we want to find out that set of data or that set of parameters which are responsible for generating the data set in our. Okay, so we are maximizing the likelihood of the data. Okay, now next is that this maximum likelihood is a kind of very similar to the frequentist approach of calculating the parameters or calculating the best parameter values. Okay, so that's why it is called as naive, you can say, estimate of the parameters or common sense estimate of the parameters. But now what is happening that I am now introducing that whether we are having some kind of prior information available for our purpose or not. So when we are having some kind of prior information available, we can encode that in terms of prior probability. Okay. Now, if prior probability we are having, prior probability distribution we are having, suppose in case of modeling the or in case of finding the best uh, probability of success or failure in case of binomial likelihood, we or Bernoulli likelihood, we uh, have the information that the the proportion of failure or success that will be between 0 and 1. That will be between 0 and 1. You know that, okay, beforehand. So this is the prior information. Now, between the 0, 1, if you want to find out the random variables value, then the best distribution will be coming into mind will be beta distribution. Okay, so when the random variable is continuous and it will be between 0 and 1. Okay, so not many distribution is having this particular property. So beta distribution will be the best distribution to model this one. So this will be the prior distribution. Okay, so this will be the prior distribution will be encoding. Okay, now this prior distribution when will be multiplying with the likelihood, then we'll be getting the posterior. Now here from I can have two, three things which is basically coming into this prior posterior framework. Okay, so prior posterior framework. So here basically we are finding out this the posterior of the what you can say. Achha, what is prior by the way, and what is posterior? So prior is the information we are having before observing the data. So prior is the information we are having before observing the data. Right now, now after observing the data, what will be the change in my prior? That will be nothing but called as posterior. Okay, so posterior is the product of likelihood and the prior. Now we can now try to find out that basically this prior is a particular distribution and the likelihood is another distribution. Now when we are multiplying those two, it is it is actually giving the posterior. Now what is the form of that particular posterior? What is the probability distribution of that particular posterior? So we are looking at basically the form of the distribution rather than the parameters of the distribution. Parameters may be anything. Okay, but what is the form of the distribution if you want to look at? Then if that form, that posterior form, after multiplying it with the likelihood, after multiplying the prior with the likelihood, if the posterior comes in the same form of the prior, then it is called as conjugate prior. And in prior modeling session, we actually looked into this particular conjugate prior, informed prior, uninformed prior, and all these things. Now, if we look at this particular beta distribution, then if the beta distribution is having actually two parameters, alpha and beta, we are talking. So, depending upon that, the shape of the PDF is actually depending. Right? Now the thing is that if both of these parameters are kept at 1, value 1, then what will happen that it will be looking as a uniform distribution. It will be looking at as a uniform distribution. So I can show you some very good graph uh, regarding that. Okay, so let us show that. Let us see that. Okay, so let me open it. That how basically step by step this binomial distribution or sorry beta distribution changing the parameters of the beta distribution, how the posterior is actually changing. Okay, so let me just open that. Some interactive graph. Okay, just one, give me 10 seconds around. You can find it out. Mm, not this one. Not this one. It's acha, acha, okay, okay. Let me open that. Uh, yeah. So, share screen. Acha. So you can see. So this is that beta binomial inference. Okay, beta binomial inference. So I'm taking prior success observations and prior failure observations. Number of success is suppose 1, if I do, then 2, then 3, then 4. Okay, so what is it happening? That suppose you are doing the coin tossing. Okay, suppose you are doing the coin tossing. Okay, so before starting the experiment, you are actually having no information regarding what is whether the probability of head, probability tail. Okay, so how does it look like? You don't know, have any kind of, you don't know about that. Okay, so what we are doing, that suppose I'm counting that heads or tails. Okay, so suppose the first one landed in head. Okay, so you have got a head. Okay, so your posterior, that is actually become a kind of triangle. Okay, it has become a kind of triangle, right? And here it is towards 1. Towards 1 means towards head. So it is telling that your head, one head has come. So second also head. So you see that posterior is actually having little curvature. Then third is also suppose head, then little more curvature. Fourth suppose is a tail. Then what will happen, that you'll be finding some kind of bulging inside in 0, towards 0. Okay, so as it has gone towards 0, so your curvature has come like this. Okay, then suppose another tail, it has come like this. Then another tail, it has come symmetric. Okay, then another tail. So it is actually moving towards 0. Just see. Okay, then another tail. Okay, it is moving towards 0. Another tail, another tail, another tail, but it is getting little spiked also. Is it okay? So the MLE estimate you can actually find out. Okay, posterior is actually the at the mode. Okay, so MAP. Then another tail. So tail, it is going like this. Tail, it is going. So in this way, suppose if you are having another head. So now you'll see that it will be moving towards 1. See, it is moving towards 1. right? Now you can actually calculate this particular depending upon number of successes and number of, so it is 6 by 21 is the probability of success, and 15 by 21 is the probability of failures. Okay, so in this way basically it is calculated. Okay, getting my point? So I can have another one, I can show you. So this is probability. No, it is here. Okay, so in this way, you can actually do little experiment on that. What should be your prior? What should be the prior parameters? Okay, and if you want to give some kind of hyper parameters of the prior parameters. So in this way, we can analyze the things depending upon the prior information available. Okay, and based on the observed data, how the belief of that particular posterior is getting strengthened and strengthened. Okay, so in this way, basically, we can do this Bayesian analysis. Now, this was the foundation of Bayesian analysis. Then what is happening? That how to calculate the posterior when there are multiple random variables. Okay, when there are multiple random variables. So calculating the posterior can be done in many ways. So one is your analytical way. Okay, so find out exactly how this how after the product of prior and the posterior. So what will be the sorry, prior and the likelihood? What will be the posterior? What will be its form? Okay, so no approximation required, and you can actually truly find out all the things. But yes, uh, uh, till you can find out the, you can calculate the marginal likelihood, till that it is okay. Otherwise, whenever you are actually omitting this particular marginal likelihood, then the approximation comes into picture. Okay. Now the thing is that there might be several ways by which you can find out the posterior parameters. Okay, as well as form of that posterior parameters, not form. So form you can actually identify by this analytical computation. So there can be sampling mechanisms, that is stochastic approximation mechanisms, and there can be deterministic mechanism also. Okay, so stochastic simulation or stochastic approximation, there we are finding all the sampling based mechanisms. In sampling based mechanisms, we are starting with that rejection sampling, then importance sampling. Then there are many other samplings like slice sampling are there. Then many other samplings which are not in, which are basically independent sequence of sampling process. Okay. Now, if you introduce this Markov chain into this, then Markov chain is actually a very interesting kind of concept, that it is telling that whatever we are today, uh, it is dependent on yesterday only, not the day before yesterday or the past days. Okay, so it is basically taking just one step back and calculating the today's state. Okay, so based on that, basically Markov chain works. Now, this particular Markov chain is having one very beautiful property, that if you go on, so Markov chain actually depends upon something called as transition probability matrix. So transition probability matrix, if you go on multiplying with itself, okay, for a long chain, then after some time, you'll be finding that all the states will be having a stabilized probability. It will not be changing over time. So maybe you'll be multiplying more and more times of this transition probability matrix with itself, but it is not going to change. Okay, so this is known as stationary probability matrix. So this stationary probability matrix actually comes after long chain of this particular multiplication. And this concept is actually exploited in case of Markov chain Monte Carlo. Now Markov chain Monte Carlo or Monte Carlo per se, it is actually dependent upon that if you sample the target function for a long uh, time or large number of samples and take the mean of that, okay, then actually you can approximate using the then you can that mean yeah, that mean is actually same as the expected value of the random variable underlying. Okay, so this is the concept which is the core concept of this particular Markov chain model or Monte Carlo better say. Markov chain is basically useful when you are having high dimensional data, high dimensional dimensionality situations. Okay,
करवाया
so
था, मैंने
there
फॉर्म भी करवाया है, वो क्या कहते हैं, जब फॉर्म हम भरते रहते हैं।
okay, so next is basically this Markov chain is actually introduced in the Monte Carlo if you are going into high dimensional situation. So it actually helps. Now the thing is that in Markov chain Monte Carlo there can be several types of methodologies like starting with Metropolis sampling, then Metropolis Hastings sampling, and then deep sampling. Then some advanced kind of Markov chain Monte Carlo are also there, where we are actually introducing the direction-based approach. Direction-based approach means that we are using the gradients of the function. Okay, we are using the gradients of the function, gradient of the functions, and based on that we are actually sampling. So that is known as Hamiltonian Monte Carlo. So Hamiltonian dynamics is actually used in that. You can use Langevin dynamics also. So all these kind of dynamics that helps us in reaching to the posterior much faster than the simple Markov chain model. Next, we have seen the deterministic approximation kind of methodology, which is known as variational inference. Now, in variational inference, basically the workhorse is the KL divergence. KL divergence, why it is used? KL divergence is actually used that it is giving me the distance between the basically what is happening that you are having target distribution with you. Okay, so that is the true posterior. That is the true posterior. But the thing is that you might not be having resources to go to that true posterior. Okay, what you are doing that you are actually you are assuming an approximate distribution for that. Okay, you are creating an approximate, you are creating the approximate distribution for that, or you are assuming, right? Now the thing is that this approximate distribution, the distance between this approximate distribution and the true distribution, that is true posterior, that will be known as the divergent. That is the distance will be there, and that distance is calculated using KL divergence, Kullback-Leibler divergence. Okay. Now Kullback, based on this Kullback-Leibler divergence, we are calculating the elbow. Okay, that is the evidence lower bound. Now this evidence lower bound is to be maximized, okay, to reach to the true or actual posterior. So we can update the parameters, okay, step by step, and we can actually have better elbow to reach to the true posterior. Okay, so we are approximating a true posterior using an approximate posterior. Okay, so in this way, basically, this variational inference is built up. Now, after that, we entered into the most, you can say, universal kind of statistical or machine learning model, that is regression. Okay, linear regression. So in linear regression, basically, this particular response variable is continuous in nature, and we try to find out the parameter posteriors, okay, using Bayesian simulation. Okay, and in that case we try to do it using MCMC kind of methodology, like give sampling methodology. We did we started with the basic one, that is the that is the our rejection sampling, then importance sampling, then Metropolis Hastings, then give sampling. All these kind of sampling mechanisms we have seen to find out the posterior of the parameters of in case of linear regression. Same thing we did for the logistic regression also. Next, we entered into variational inference, in which we try to approximate the or you can say the find out the posterior on the parameters using this deterministic approximation. by finding out the updates of the parameters as well as by maximizing the L. Okay, by maximizing the lower bound. Okay, so in this way, basically, we have seen this variational inference also. Then we entered into this particular neural networks. Now, neural networks are basics, and we have seen, and this particular along with the basics, we tried to solve a particular a small neural network and try to find out the how these particular updates of the weights are being done using this propagation algorithm. Now, Bayesian and neural network I wanted to cover, but I think we should stop here because it will be very heavy for you to digest all the things. So I'm not going to start that Bayesian and neural network. I'll be stopping it here. Okay, so I think this is a recapitulation of this particular the topics what we have covered till now. And now after me, then Dr. I should be coming out. I should be completing that particular data visualization. And for that, there will be no recording, no broadcasting also on YouTube. So you please stick with the this thing lecture, and he'll be actually helping you to understand and everything. But you will please this will not be recorded. Okay, this lecture will not be recorded. Okay. So anybody is having anything, any feedback, anything to say? Mr. Amar?
Oh, sir, thank you. Thank you very much.
Thank you. Acha, Pratik?
Yes, sir.
So anything you want to say?
Sir, I felt it was mathematically very heavy.
Sorry, I'm not
It
getting.
is mathematically heavy.
Mathematically heavy. So
Yes, sir.
actually, I planned it mainly for research scholars, PG students, and advanced level UG students who are interested in this understanding the mathematics of this probabilistic machine learning development.
Mm-hmm.
Okay.
Yes, sir.
Yes. So later I'll keep this in mind. Diluting little bit. Okay. Or,
Sure, sir.
yes. We'll be reducing the mathematical rigor little. Yes. A little more. Okay. So anybody else? Dr. Ruchita? Naveen, training session is very good, but the course is lengthy and we're not. That I can understand, Naveenji. That I can understand.
Sir, again, sir, I am asking to where to start again, sir. There are a lot of mathematics and other things are there.
Yes. Okay. So there are two very good books. So I'm sharing it with you. So as I told, one was that Bishop, Christopher M. Bishop. So let me just let me change my this thing. How to change this background? So, change virtual. And this is mirror image it is putting. How to change it to okay, so this book is by Christopher and Bishop. Okay, this book is Pattern Recognition and Machine Learning by Christopher M. Bishop. Okay, and another is another is Machine Learning, a Probabilistic Perspective. This one, Probabilistic Machine Learning. Okay, by Kevin P. Murphy. Okay, just 1 minute. Let me change this. So, okay, this one, Probabilistic Machine Learning by Kevin P. Murphy. Okay, this one and this one. Pattern recognition and machine learning. I don't know how to change the mirror thing. Oh, acha, got it. So this one, pattern recognition and machine learning by Christopher M. Bishop. Okay, this one and this one, probabilistic machine learning by Kevin P. Murphy. Okay, so these are the two books which are very, very good. But you can actually, you should start with this one, Bishop's book. You can start with this. You should start with this Bishop's book. Okay. And another one is that for understanding Bayesian statistics, you can actually start with this one. You can start with this one, Peter T. Hoff, first course in Bayesian statistical methods. To start, Bayesian methodology. Okay, Bayesian is very, very interesting, and it is having R codes given in this particular book. Very, very interesting book. Okay, and very thin book, hardly 200, 300 pages. Okay, 250 around. Okay, so you can finish it very fast if you are interested, right? And this will really create your the Bayesian literacy. Which one? Last name. Last one. Last one is Peter D. Hoff. This is also freely available over net. Okay. First course in Bayesian statistical methods. Peter D. Hoff. Okay. 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 So Peter D. Hoff. Yes. So anything else? Anything else you want to ask?
Sir, I also want to know that whatever you have covered in this workshop, is any research article using similar article if you find
Lots of
very
research articles. Yeah, Kevin P. Murphy, Probabilistic Machine Learning by Kevin P. Murphy. Yes, lots of research articles are there. Lots of.
So you can suggest some of the very simple,
Acha, okay,
easy to digest.
that is the main problem. That is the main problem. So problem is that you are not that much receptive right now. Okay, to understand those concepts and all these things. You need to have very good, thorough, you can say, understanding of Bayesian statistics first. Okay, so in application wise, it is having lots of applications. Okay, lots of applications. And Bayesian statistics, as I was telling, that it is having much more, you can say, concrete framework. Okay, the framework is quite good, and you can have the same kind of model that can be your supervised learning, that can be your unsupervised learning. Okay, that can be in deep learning.
Sir,
So
Bayesian statistics, for Bayesian statistics understanding, you have mentioned third one book, na?
third book,
What was
yeah,
name?
Peter D. Hoff. Peter D. Hoff.
Okay, okay. Yes, yes.
Okay, this one. So, if you are interested in delving more into this, so acha, another thing is that many of you are not really having any exposure to machine learning, I think. Many of you. Can anybody tell how many of you? Just raise your hand. Okay. No exposure. So, acha, so let me stop this video. Shinu, can you please stop this video? Nazira, okay.
Which video है?
So, what I'm telling,
सर कौन सा वीडियो?
video जो recording, yes.
अच्छा, okay, okay, done.
Yeah, okay. So, what I was telling, that if you are interested in learning this machine learning, so I can tell you some very good starting for beginners. Okay, so kind of I'm telling you. So you can find out this Python for machine learning, I think.